for the camera, which has come late for this class. We're just clearing up. We're just clearing up. Thanks, guys. No, it's no problem. We're just clearing up confusion from last class about the index structure of this integral equation. So we're defining m alpha beta to be psi alpha psi bar beta in the presence of one insertion of psi bar. G alpha beta, the exact propagator to be psi alpha psi bar beta with the presence of zero insertions of psi bar psi, just the exact propagator. Okay? And with these definitions, it's not difficult to convince oneself that the right structure of the integral equation is this: that m is equal to m0, g gamma minus m gamma minus g. That's the right index structure where multiplication is just by matrix multiplication, where you treat the lower index as the first index and the upper index as the second index. It's just straightforward matrix multiplication of this object, where an m0 is just g times g. Okay? Now, as we look, when we get this index structure here, it's clear that the only part of m that can contribute is the part proportional to gamma plus. We'll call the coefficient of m that is proportional to gamma. M could be anything, but the only part of it that appears on the right hand side is the part proportional to gamma plus, and we call the coefficient of that m minus. Okay? So the only thing that appears on the right hand side is m minus. So if we want to solve the equation for m, let us first solve the equation for m minus. Once we have m minus, to determine all other components of m is trivial, because we just have to work out the right hand side. Once we know what m minus is, then m is determined from this equation. This equation is a complicated equation because the unknown appears both on the left and the right hand side. But as we've seen, the only part of the unknown that appears is m minus. So once we know m minus, our problem is easily solved. So it boils down to just determining m minus. Okay? So we're only interested in the minus component. So we're interested in the part of this equation that is proportional to gamma minus. So what contributes is the part proportional to gamma plus. Gamma plus. Right. So we want the part proportional to gamma plus in this equation. You remember, as we argued last time, for the singularity we can forget about m0. We just need this homogeneous equation. Okay. So we want the part proportional to gamma plus. When you see this term, even if we take the part proportional to gamma plus here, for the whole thing to be proportional to gamma plus, we need the part from G that's proportional to gamma plus, and this G also proportional to gamma plus. So that we have 3 gamma pluses, 2 gamma minus, so that the net charge is plus. So the whole product will be gamma plus. Okay? And that gives us exactly the equation we wrote down last class. See, the part proportional to gamma plus here comes with k minus. Part proportional to gamma plus here comes with k minus. You look at your notes, that's the equation we wrote. We took the part of the propagator for the fermions proportional to gamma plus, the part of the propagator fermions proportional to gamma plus, and just multiplied it through. And that gave us the integral equation that we wrote down in class. Okay? This integral equation that that had a factor of p minus minus r minus and p minus in the numerator, because the part p minus came from p minus gamma plus, p minus minus r minus came from p minus minus r minus. Is this clear? Okay. So this. Okay. Once we've solved for m, and the key point is that this is the only non-trivial solving process. The only place where you have to invert something, and thereby the only place from which you can get a singularity. Okay? Once we've solved for m minus, all the other components of m will be easily determined, and the procedure that determines them has no possibility of generating new singularities. So all singularities in the two-point function can only come from singularities in the solution for m minus itself. And therefore, if we are interested in the spectrum of the theory, we need only study the singularities of the operator of this n minus, or in other words, the zeros of the of this homogeneous orbit. Is this clear? Questions, comments? Okay. By the way, if we didn't want to throw away this part, it would be easy to keep. We just keep G, G, K minus, K minus. Okay, just keep the part proportional to gamma plus from here as well. Okay, we're not interested in that, but that would also be easy to keep. Okay, so this just justifies the calculation we did in class last time. Everything else we said about the integral equation is correct. There's something I got confused about with the index structure, which I hope we've cleared up now. Any questions or comments about this? Okay, let's complete our analysis of this model, and then I'll come back to the second confusion we had last time about the derivation of the Lehmann representation. But just to not break the discussion, let's finish this discussion and then come back. Okay, any questions or comments about it? Sorry for the mess up last time, that was not a good thing. Sorry about that. Okay? Excellent. So, now at the end of the last class, we had achieved the following integral equation. You remember that we called the coefficient of this gamma plus in M, we call that coefficient psi, and then we take a certain integral of this psi, an integral over p minus or p plus, p plus, or integral over p plus, and we call that phi. Everyone remembers this? And we had an integral equation for this phi. And you remember that we processed that integral equation, and one very nice thing happened. The very nice thing happened was that there was a new singularity in that integral equation. A new IR singularity coming from an integral of phi with a 1 over p minus squared. That had a new singularity at the denominator of that kernel, and then we wrote that kernel as that integral, which was just some integral. Is this making sense? Everyone's actually looking. No, people don't remember this? Yeah. You remember we had that there was an equation. Firstly, you remember that phi, by pole manipulations. Okay, let's just remind you. Okay, so there's this exact M. It has a momentum that runs through, which we call R, and then the division momentum. Okay, so if we call this momentum P, this was R. R was constant at each step in the integral equation. R was just constant. R was not a variable of the integral equation, it was just a constant. P was a variable of the integral equation, because if you've got this guy here, then you look at this, if this is some P, this would be some other P, and the P is being integrated. Okay? So it's like a matrix equation where the matrix variable is P, and R is a number. Okay? And what we had found was the integral equation phi of P minus R minus was equal to G squared by 2 pi theta of P minus theta of R minus minus P minus times integral phi of P minus plus K minus or over K minus squared dk minus divided by m squared by 2 P minus plus m squared plus m squared by 2 R minus P minus plus G squared by pi lambda plus R plus, where Lambda was the infrared cutoff. You remember we were taking the integral and just stopping it where the propagator, the gauge boson propagator, the momentum the gauge boson propagator reached lambda. Okay? This was the infrared cutoff in our exact computation of the propagator. What was capital M? M square was the effect of renormalized mass. Was it? M squared minus G squared by 1. You remember when we solved for the gauge boson propagator, for the fermion propagator, we got one correction term that just renormalized the mass, and then the other correction term that was infrared divergent. Okay? So now we're working in terms of this renormalized mass. And then we have this additional ugly infrared divergent case. Okay? So n squared is written in terms of the bare mass squared where this object is. This was the integral equation we got. Someone remind me where we get this theta p minus theta r minus p. Somebody? Why? Somebody, where do we get this?
Positivity of energy and R greater than
Where the positivity are in? Go on. Yes, go on.
Since R is the total energy, means R minus is the total energy you want at each P minus you want R minus to be it will be greater than P minus.
You give it a good physical interpretation, but we got it from mathematics. How do, what you're saying is actually completely right. But where did we get it from? We got it at a certain step. You know, in the integral for psi, in the integral equation for psi, we had no thetas.
Yeah.
We got a theta function when we moved to the integral equation for phi. Okay? What did we do in going from the integral equation for psi to the integral equation of phi? We integrated over p plus. Now, you see the integral equation on the right hand side has these two fermion propagators. And we have p plus enters only in those two fermion propagators. Because the gauge boson propagator was entirely a function of p minus. Okay? So we have to integrate the two fermion propagators over p plus. But now look. Remember, because we're working in light cone variables, the denominators are linear in p plus. If we were working in ordinary time, the denominators would have been quadratic. But p squared is p plus p minus. So it's linear in p plus. Right? We've written out updated. There's denominator is linear in p plus. So what we've got is a product of two poles. And we did the integral by contour means. But remember that the coefficient of p plus was p minus. So we got p plus into p minus, and then we had r minus, let's say p plus minus r plus into p plus minus r minus. And this was Sandara plus I epsilon. This was Sandara plus I epsilon. And we were doing integral dp plus.
pole inside the contour.
Exactly. Now the point is that if P minus and P plus minus or minus are of the same sign, then both of the poles on the contour go either above or below the contour. And we can always evaluate the contour integral by closing the contour the other way. So we get 0. Of course, you could evaluate it by closing the contour this way. And then what you will find is that the two pole contributions will magically cancel each other. As you can prove by evaluating the contour the other way. Okay? So this thing is 0 unless P minus and P minus minus R minus are of different signs. Now, we are interested in this integral equation for some fixed R minus. So we could just concentrate on one particular, we have to look at both possible signs for R minus. But of course, in the end, we're looking for physical singularities. So R minus is the center of mass entity. Okay, so we'll want that to be positive in the right dimensions. Right? So we choose R minus to be positive. And then, how can these two guys have different signs? The only way it could have different signs is if P minus is greater than 0, but P minus is less than R minus. Okay? In which case, this guy would be positive, and this guy would be negative. Okay? And that gives us P minus greater than 0, P minus less than R minus. That gives us those two theta functions. So, outside that region, that integral which is 0. Okay? Inside the region, we got something non-zero. Clear? And then we evaluated that integral. We got this quantity. Then the next thing we did was take this guy to the left-hand side. Okay? So this becomes now some nice looking integral equation for it. So you get some homogeneous part, something multiplying phi is equal to theta times some integral. And then we notice that this quantity was a divergent quantity in general. Because what does it mean? K minus square goes up. It's not an integrable singularity. Okay? So we have to give meaning to that. The quantity near K minus equals 0. And of course, since we've given meaning to this quantity when evaluating the propagator, we should give the same meaning here. We get the same meaning. We just stopped the integral over K minus at lambda. But, so you get some result. But as we will see in 2 minutes, what is convenient for us is to study, is to give a different definition to this integral of K minus. So what we did was to say, well, we can relate this definition, what it physically is, to what is mathematically convenient by subtraction. What was mathematically convenient was to regard this integral as the average over two contours. One which skirted the singularity from above, and one which skirted the singularity from below. And we deduced last time that the difference between the physically relevant prescription and the mathematically convenient one was some quantity that went like 1 by lambda. We deduced that by computing the contribution from this contour and this contour, adding them up. Okay? And when we did that, we noticed that lo and behold, that difference which appears on this side exactly cancels this g squared by pi lambda multiplied this way. And so we finally got an integral equation that, written in terms of these integral over average contours, had no reference, made no reference to this IR cutoff. Because IR cutoff has disappeared in the final answer, in the final expression for the integral. Okay? Any questions or comments about this? Okay. And then, okay, it's nice of you guys, you spend 5 minutes before, 10 minutes before class reading through your notes, okay? Just to jog your memory of what's going on. Okay, yeah. Okay, and the final integral equation we achieved through this whole process process was minus r plus of phi of p minus times r minus is equal to m squared by 2p minus plus m squared by 2r minus 3 minus phi of p minus r p minus r okay. Is equal to e squared by 2 by principal value of integral phi of p minus plus k minus okay. Now, so this is the final integral equation. Now we want to understand this equation a little bit. Okay. So the first thing we do is to define some new variables that are self-convenient. Let's define the variable p minus divided by r minus is equal to f. Now remember that p minus ranged from 0 to r minus because of those two theta functions. I have not written the theta functions in this form yet. And then equal to 0 to plus. Maybe it's a minus. I'm not sure of the sign. Okay, yeah, but okay. So you remember that I've not written the theta functions. Okay, this integral equation is only valid for that range of p minus that lies between 0. Outside phi is just 0. Okay, so p minus divided by r minus is this variable x. What does x range over? X ranges over the 0 to 1. Now, what we see is that every side of this equation scales like r has positive charge plus 1. Okay? There's plus 1 here, blah blah blah. Let's make the whole equation neutral just by multiplying through by r minus. We get r minus here, r minus, and here an r minus. Okay? Now, r minus divided by p minus is 1 by x. This it can also be written in terms of 1 minus 1 by x. Okay? 1 minus 1 by x. And here we make a change of variables to the x variable. Okay? So we call r minus divided by p minus x, and k minus divided by p minus we call that y. K minus divided by r minus we call it y. When we make the change of variables, since there was a d2k, which is a dk minus divided by k minus square, this was also of 1 over minus charge. So we get a 1 over r minus out when we make the change of variable. We should cancel that. Okay, so the whole equation becomes neutral and can be written as minus r plus r minus phi is equal to m squared by 2x m squared by 2 into 1 by x plus 1 over 1 minus x minus g squared by 2 pi principal value of phi of I'm not writing, okay, there's an r here, phi of x plus y over y squared. And dy. Now let's look at dimensions. this is that every quantity here in 2 dimensions, g squared has dimension of mass squared. Can somebody explain this to me? Somebody explain why is g squared dimension mass squared?
Because m square was like the renormalized mass density at some quantity.
That's good, that's good. We're just on the Lagrangian of 2D angles theory. Why is g squared dimension mass squared? What's the dimension of the field strip? What's the dimension of A? The dimension of A is 1. A is what enters the covariant derivative. A enters like del plus A. Okay? And so A has the same dimension as a derivative. Okay? In the conventions where we are taking 1 over g squared to lie entirely outside the action. So A is dimension 1, so f is dimension 2, f square is dimension 4, d2x is dimension 2, whole action has to be dimensionless. So it has to be multiplied by quantity of length squared, but we multiply by 1 over g squared, therefore g squared is mass squared. Okay? So g squared in 2 dimensions is dimension mass squared is dimension mass squared, and momentum squared is dimension mass squared. Okay, so we can divide this whole equation through by g squared. Okay, this quantity is mass of the excitation. R plus R minus, okay, is the mass of your state, is the mass of the excitation in units of g squared. This quantity is the renormalized mass of the problem in units of g squared. Okay? And this quantity here is whatever it is. Okay? So now this equation here is an equation, is like an eigenvalue equation. Okay? Such that the eigenvalues will determine the allowed singularities, mass singularities of the problem. So it's an equation which we want to solve for. We want to find solutions phi that obey this equation. And as often is the case, we will find. The question is, are there solutions for phi for every value of r plus r minus? Or only special values of r plus r minus? Okay? So Toft calls this quantity, he has some name for this, he calls this alpha. No, sorry. He calls it mass squares. He calls this guy he calls alpha without the 2. So m squared by g squared is alpha. And the quantity that we're actually interested in, which is minus 2r plus r minus divided by g squared. For some reason equal to pi, he calls this equal to mu squared. Okay, alpha and mu are now dimensionless, obviously. And so you can rewrite your integral equation as mu squared phi is equal to phi of x is equal to alpha into 1 by x minus 1 by 1 minus x minus principal value of phi of y, y minus x the whole square. Very nice, neat, compact form of this equation. We're looking for we want to know what are the solutions to this equation. Are there solutions at every value of mu square or only particular values?
Why are we calling that mass of the excitation? R plus R minus?
You see, why are we calling that? You see, because what we are interested in is the singularities of the 2 point function. What we were interested in was the 2 point function, and we wanted to know what its singularities were as function of its center of mass. central mass momentum is r. From Lorentz invariance, the singularities of the two-point function can only occur at special values of r square. R square is r plus r minus. Okay? And as we reviewed last time, singularities are of two forms. There are poles or cuts. Poles occur at special values of r plus r minus. Okay? Cuts occur at ranges of values of r plus r minus. Okay? So, what we want to know is what the singularity structure of this two-point function is. You remember we argued that the singularities of the two-point function only occur at when you have solutions to the homogeneous part of the equation. But solutions to the homogeneous, this is the homogeneous part of the equation. So, solutions to this equation give us singularities of the two-point function as a function of r plus r minus. Is this clear? So that's what we're after. We want to know what we're after physically is what values of r squared will the two-point function have singularities at. And the answer to that question is exactly those values of r squared such that this is a solution to this equation.
That justifies calling it a mass, but why? What excitation are we talking?
What excitation? You see, it's the excitation that runs in the middle here. If there are poles, these poles will reflect the fact that there exist propagating particles. If there are cuts, this will reflect the fact that there are propagating multi-particle states. Okay? So every singularity is associated with some on-shell excitation. Okay? And you remember we started this exercise because we wanted to check whether or not there were cuts. Can somebody tell me why lack of confinement would imply cuts in this process? What is the answer for this two-point function? And what is the answer for the singularity structure for this function? This two-point function in field theory?
You should have branch cuts.
You should have only branch cuts. No poles, only branch cuts, because side by side produces two particle states. So, naive perturbation theory would lead to the expectation that we have two particle states, or cuts. So, naive perturbation theory would lead you to expect that this integral should have solutions at every value of r plus r minus above a certain mass threshold. Okay? That's what we're checking. Is this clear? Okay. So, now this is a well-defined integral equation. Actually, there's one question about the boundary condition. This x is only defined between 0 and 1. Some question at what boundary conditions to impose at 0 and 1. Now, this actually has been a subject of huge discussion in the literature. But this discussion was entirely avoided by Tove, who gave some arguments, which turned out, of course, to be right. And the simplest argument is that we've got these theta functions, okay? So phi vanishes on the other side of 0 and 1. So it would be very weird if it didn't vanish as it tended to 0 and 1. So if you just didn't think too much, you said the natural boundary conditions for this phi is that phi at 0 is 0, phi at 1 is 1. And there's enormous amount of discussion of this question, but that turns out to be the right.
Phi at 1 or should it be 0, right?
No, so phi at 1 is 0, sorry. Phi at 0 and phi at 1 are both 0. There's enormous amount of discussion in the literature about why it's right. Tove even has a footnote in his paper saying this will not be the last word of this this question, and he was very right about that. Okay? We'll, at this level for this class, we'll forget about that. It sounds reasonable, right, to put these boundary conditions.
Sir, the first one on the right hand side also blows up at 0 and 1. So, won't that create some?
Won't that create some problems? Right. First term on the right hand side also blows up at 0 and 1. Yes, that's right. But so does this. Yeah. So does this because you see, this thing here has 1 by x square singularity if you set x equal to 0.
Y equals.
why is an integration variable? We set x equals 0. Hang on for a minute. Hang on for a minute. You see, you'll see. It'll become a bit clearer. Okay? Yeah. For the reasons for the kind of reasons you're mentioning, there's been a lot of discussion of these boundary conditions. Hang on for a minute to see what we do with this, and then we proceed. Okay. Now, the question is, what are the right? How do you solve these integral equations? Nobody's managed to solve these integral equations analytically. Okay? And it's not difficult to solve them numerically. Actually, Toft himself did some numerical analysis in his paper. But the most elegant thing in this paper is to just look at first at a WK square. Okay? So, suppose we look at the limit of, well, these are the kind of issues you're talking about. Suppose we manage. You look at the limit of very large mass. Mu square is very large. Okay? Now, if mu square is very large, these terms here, at least the generic values of x, can be ignored. Because alpha is something fixed, mu square is very large. Okay? So this looks like the dominant term of competence. So it's plausible that what you're doing is solving an equation where this guy is balanced against this guy at the limit of very large mass. Okay? Now,
but sir, I find it a little hard to answer because at x equal to 1 or 0, like no matter how large mu square is, the first term is equally large. It's like
well, let's look at every value of x. This equation has to be satisfied at every value of x, not just 0 and 1. Look at values other than 0 and 1.
Then it's fine, but
we have to worry about how the boundary conditions. We have to worry about what happens at the edges. But everywhere else, it's okay, right?
Yeah.
And then you have to factor something.
Yeah.
Okay, so let's leave the considerations of boundary conditions aside. Okay, apart from at the boundary, this is somehow very reasonable.
Yeah.
Okay, now the second thing that we have to understand. Now the other thing that Toft pointed out was that look at this object here. Remember, we're defining it with this principal value. Now, one of the things I want to show you is that this principal value definition removes all possible singularities. So I told you that we got rid of intra-net divergences, but we got rid of it by some sort of trick. Okay? The trick was rewriting what was an integral in terms of principal values. And this would not really be getting rid of intra-net divergences if the principal value integral itself diverged. Okay? So just as an example to say that this principal value integral does not diverge. As an example, let us evaluate the following. Let us evaluate the integral minus infinity to e to the power I omega y y minus x over x squared dy. Just to try to understand how this principal value integral. Okay? Let me just try and see what we get. Okay.
Did we not have just y square in the denominator?
But
Where did we get y minus x squared?
okay. Where did we? It's some shift of variables.
We had a worthless x inside.
Yeah.
Oh, I see. Okay.
Yeah. Okay?
Yeah.
So now let's look at this. You see, whenever we got integrals of this sort and we got some nice contour prescription, we always evaluate the integrals by contours. Okay? So, what have we got? We've got a contour. We've got an integral like this with a singularity here at y is equal to x. Okay, so let's say x. It doesn't matter. X positive, negative. Will not matter. Positive and negative will not matter. So there's some x here, and we've got one contour that goes like this, and another contour that goes like this, and we evaluate the average of the two. Okay. Now let's look at the various cases for the sine of omega. Suppose the sine of omega is positive, then we are allowed to close the contour like this. So this part of the contour does not contribute, but this part does. So suppose sine omega is positive, then we get e to the power I omega y half integral minus infinity to infinity over only this contour y minus x the whole thing square. Now we're going to use Cauchy's theorem. Cauchy's theorem picks out only the poles. This is a double pole, so to get the pole we need to differentiate this. We need to Taylor expand this function near y equals x. Okay? So when we Taylor expand this, this is half of e to the power I omega x plus I omega e to the power y minus x e to the power I omega x over y minus x the whole thing square. Okay, this part doesn't contribute, this part does because it gives you a pole. And the contribution of this is simply 2 pi I times e to the power I omega x. Okay, times I omega. Yeah. No, I'm doing the integral over y. Over y. So you pick out the contribution at the pole. Right? So you get it to pi omega x. Until x happens. Okay. So this is equal to minus omega, and there was a half, minus omega pi and pi omega x. Minus pi omega. Okay, good. This was when omega was positive. What do we get when omega is negative? Exactly. When omega is negative, the only thing that changes is we have to choose the other contour. The other contour, well, this contour is clockwise, counterclockwise. The other contour is clockwise. So it picks up an additional minus sign. So we get exactly the same thing as this, except with an additional minus sign. So the full answer is just this for the mode. Okay? And so the integral of this quantity, first thing to notice is that it's finite. How can it fail to be? You see, it's got a pole-like singularity somewhere in a contour. No matter how close that pole approaches the contour, there's no possibility of a singularity. You just get the contribution from the pole. To say it again, in complex analysis, if you've got a contour like this that hugs this, with some singularity that is polar, pole to some power. By Cauchy's theorem, you can always deform the contour to this. So it's clear the contour approaching singularity is not a singularity. Because it's meaningless. Okay? That is the reason why we changed this integral from integral over these cutoffs to integral over contours to ensure that these integrals will not be singular no matter if we took this epsilon to 0. You understand? This is a very important point. It's a trick used all over many areas of physics. Very important. And of course mathematics. But it's a very important thing. The contour integrals are generically non-singular. By the way, just as an exercise, when can contour integrals get singular? Are contour integrals always non-singular? No. They can get singular. You know when that can happen? When two poles approach the contour from different sides of the contour. Because now we can no longer move the contour away to be far away from both singularities. This is called a pinch singularity. Contour integrals get singular basically in two situations. A, if they get pinched by singularities from opposite sides. And B, if the contour integral is not over some infinite contour but a contour over the boundary, and the singularity approaches the boundary.
Sorry, why don't you just take it above?
When this,
Which case?
show me how, can't go through a singularity.
No, just go above that.
Go above. And this is my contour. Now how should I move? I can go like this. But if I go up through here, I go through a singularity.
So like that is your original thought. I'm just not getting it.
Yeah. This is the integral. Yeah. We can now use Cauchy's theorem to turn it into some other mathematically equivalent object.
That's okay. So like the way we do it for this thing,
Yeah.
you can just go above it.
No. You can only go above it. You can only deform the contour over a region where the function is analytic.
Yes.
So you're allowed to deform the contour through regions of analyticity. But you're not allowed to deform the contour through any singularity. Okay? So you can take it above, but then you will be left with the contribution of the singularity in this pole. And this pole will give you a singular contribution.
Yes.
Because its residue will be singular, because it will get the contribution from this nearby pole. Is this clear?
Yeah.
So, pinch singularities are genuine singularities of contour integrals. And boundary singularities, when you've got a fixed boundary that you're not allowed to change. You're going to integrate from here to there. And a singularity approaches that boundary, that can often be a genuine singularity. But singularities approaching from one side, approaching the contour from either above or below, are just fakes. That's what Toft has used. Okay, so first thing we see is that it's non-singular. But the second thing that we see is that this function here, e to the power I omega y, okay, if we were worrying about the integral not from 0 to 1, but from minus infinity to infinity, is actually an eigen function of this kernel. That is, you take the function e to the power I omega y, you act with this integral expression, and you get back the function e to the power I omega x. Okay? This is true only if this integral goes from minus infinity to infinity. Okay? Because these contour methods need that. It's not true for the integral from 0 to 1. But let's look at this integral in the limit omega is very large. Okay. In the limit that omega is very large, this integral here, it's going to get contributions you can evaluate by saddle points. In saddle points, it will only get contributions where the derivative of this function, which is omega, is balanced against the derivative of this exponential, this e to the power minus log, balanced against the derivative of that log. Since omega is very large, you can only get contributions where y is very near x. Okay? So in the limit that omega goes to very large, this function gets its dominant contribution from the region y near x. If that is happening, provided x is not near 0 or 1, once again we're staying away from your boundary points, okay? Provided that x is not near 0 or 1, it makes very little difference whether you're integrating y from 0 to 1 or minus infinity to infinity. Okay? Because let's say that x is somewhere here, this is 0, this is 1. All of the dominant contributions coming from here. So when you integrate from here to here, here to here, here to here, or minus infinity, in the large omega limit it will make very little difference. Okay? So, in the large omega limit, okay, this integral equation which now I rewrite, the integral equation that which now I rewrite, which was mu squared phi of x is equal to alpha into 1 by x plus 1 over 1 minus x phi of x I should have sorry, I should be more systematic. Minus principal value of integral phi of y minus x the whole thing square has very simple structure. Because in the limit of large omega, we can take any function which obeys the boundary conditions that vanishes at 0 and 1 and expand it in a Fourier series. Okay? So, any function phi of x can be written as sum over n sine n pi x and alpha. That of course is general. Okay? But the point is that sine n pi x is e to the power I n pi x minus e to the power minus I n pi x over 2i. And we saw what this integral operation did in each of these functions. It just gave us the factor. What was it? Can somebody remind me? I dropped it off.
So it splits into two eigenvalues.
Hang on. Let's just evaluate this. We plug this in and evaluate it. Okay? So we just plug in that phi of x is equal to this.
Sorry, what could we do that?
Because we're looking at this is the basis for functions. We're looking at functions that are 0 at 0 and 0 at 1. Every such function can be expanded in a Fourier series.
Okay.
Maybe I
got it. No. Yes.
Right?
Yes.
Okay? Now, if we plug this in, can somebody remind me what y
Yeah, it's minus omega, mod of omega pi.
Well, was there some I?
No.
Minus pi mod omega times itself. It types it I omega I. So, suppose we put this function, what do we get? We get minus pi times mod omega is n pi. For both of these, because mod doesn't change. Okay? So in this basis, what do we have? We have that this equation becomes, let's take the coefficient of sine n by x. We get mu square is equal to, we're ignoring this, because that's small compared to anything else, we ignore that, is equal to n pi times minus, but minus goes away because that's minus, plus n pi. So is equal to n pi square mod n pi. Okay. So if we just plug this in, what have we got? We've got alpha n times mu square minus n pi square. Sum over n is equal to 0. That's our equation. This equation has obvious solution. That's a diagonal equation now. So its solution is mu square is equal to mod n pi square. These are the eigenvalues and the eigenfunctions. First one is sine n pi x.
This is very similar to what we do in quantum mechanics with particles in a box.
Particles in a box, except that it's a bit unusual to have this non-local kind of potential. Yeah, but you're right. It's very special. It's not even that unusual. Yeah, it's just.
In the way of getting the spectrum of eigenvalues.
Yeah. This is basically a Schrodinger equation. This is basically a Schrodinger equation with some effective potential.
So can we take the first term as a perturbation on the...
Right. So as we take omega away, the only thing you have to be careful about is dealing with, as you have pointed out correctly, dealing with the boundaries. You'll have to be a bit careful about what you do. But one can systematically expand away from this, and in fact I think you may have done that. Yeah. So I won't try to work this out, but Toft has tried to find the first corrections. Okay. So in a large So you get n squared n pi squared plus 2 alpha times log n plus. Okay, so it's not just some extreme large. You can systematically correct this. Okay, now there are many things to notice about this answer. The first thing to notice about this answer is that the spectrum is continuous or discrete. Discrete. Mass squared is proportional to n. This is what's called a Rege trajectory. Mass squared is an integer. This is a Rege trajectory. This happens all the time in string theory. Okay. Second thing to notice about what is the spectrum of psi bar psi acting on the vacuum in this theory? A bunch of single particles. There are no multi-particle states in psi bar psi acting. Contrast this with what happens when you act psi bar psi in the vacuum in the free theory. You get only multiple particle states. Okay? Secondly, how many single particle states do we have? Infinity. Okay? This is an artifact because of the large n. This spectrum of multi-particle states will truncate at some number that has to do with n. Capital N. But we work with the strict large n limit. We don't say this. For us, this goes up to infinity.
Yes, just one question.
Please.
There's mod n which was inside a summation over n.
Yes.
How do you do over the summation? To equate mu squared to n pi squared?
Yeah. Let me just present this whole thing a little more systematically. There's something
I understand all of it. That on the right hand side you have a summation n mod n.
That's here.
Yeah.
This is the final equation.
Mu squared. Okay. Sorry.
Right? So I get the equation condition that either alpha n is 0
Yeah.
or mu squared minus mod n pi squared is 0. This is the structure of eigenvalues.
Yeah.
Sir, can you just go through the conclusion again?
The conclusion is that this integral equation has singularities only and mu square is equal to pi square times n. And large mu square. Okay? Now compare this to what would happen in the free theory. In the free theory, that integral, and there won't be an integral equation, there's a 2-point function would have singularities. And every value of mu square larger than 4m square. Because the spectrum of two particle states. Okay? The fact that we do not have a continuum, that we have solutions to this equation, therefore singularities of the 2-point function, only at discrete values of mu square, tells you that there are no, that psi bar psi does not create multi-particle states. Okay? That tells you, or that is consistent with the fact that we also saw by looking at the particle, that there are no single particle states created by psi. Because if there were, then surely psi bar psi would create multi-particle states.
So it's just a manifestation of confinement.
It's just a manifestation of confinement. Okay? So what's going on? What's going on is that in the free theory, that this particle going this way, this particle going that way. But in the interacting theory, there's a force between the particles. Now the force between the particles is like that of a rubber band. Okay? It's a force that grows larger and larger and larger without limit as you take the distance between the particles to infinity. And therefore gives you a discrete spectrum. All this is familiar from non-relativistic quantum mechanics. See, suppose you've got some sort of, in non-relativistic quantum mechanics, you've got some sort of potential that is like this. What is your spectrum? We have a few bound states, and then you have scattering states. So you've got a continuum along with some bound states. Okay? On the other hand, if you've got a potential that is like this, what do you have? Only bound states. going like that. What's happening is that there is some effective force between these quarks being developed that keeps going off to infinity, giving you only bound states. Okay. Now, this sounds very dramatic, okay? And it's very beautiful solution, like beautiful model. But I just want to emphasize something that is clear from the beginning, but it's less dramatic than I may have seen, because in the particular case of 1 plus 1 dimensions, the Coulomb force. Okay, so in 1 plus 1 dimensions, so let's remind ourselves. The force law in 4 dimensions, the force law between two, the Coulomb force law in 4 dimensions, is a force law that goes like 1 over r squared. In 3 dimensions, the Coulomb force law is a force that goes like 1 over r. In 2 dimensions, the Coulomb force law is a force that goes like that is like log r. In terms of potential, in 4 dimensions, the Coulomb force is like 1 over r. In 3 dimensions, Coulomb potential is like log r. In 2 dimensions, the Coulomb potential grows linearly like mod r. Okay? So even classically, the Coulomb potential that is there between quarks and antiquarks, okay, is an ever-growing potential. Okay? So the phenomenology of a hydrogen-like atom in 1 plus 1 dimensions would be very different from 4 dimensions. Because even classically, there is this force that grows without limit. So it's not too surprising. But the same feature persists quantum mechanically, though we've seen it with much more precision and much more sophisticated way than the rough classical analysis would allow. But this is not too terribly surprising. Okay? The point, however, is that it is very strongly expected that the same thing happens in 4 dimensions in the quantum problem, even though classically the 4-dimensional force falls off like 1 over r. 4-dimensional potential. Okay. So this is a template for how the 4-dimensional quantum theory might work. But it's not that surprising by itself. Because, if you were going to be a bit cynical about this, you'd say, well, okay. Classically, I see this potential rising. Should I be surprised? Shouldn't be surprised. But it's nice that you can work it out in such great detail. Okay. The other thing to notice about this is that the spectrum of masses, the leading order is independent of the mass. Okay. Independent mu squared, which is the mass square of particle of the excitation divided by g squared, was mod n times pi squared, was independent of this alpha. Okay? As you see, the first correction starts depending on alpha. Okay? So, the thing this emphasizes is that the generation of this dynamical mass scale, the mass scale that sets the scale of masses of at least very heavy particles, is the gauge coupling. It has very little to do with the fact that the quarks were originally massive. It's irrelevant. It's a detail, irrelevant detail. Okay? The genesis of the mass is in gauge interactions, not in the mass of the quarks. Okay? That's another feature that's very expected to be true of ordinary QCD. If ordinary QCD you had massless quarks, we would have some massless splitting in the pions. But all the other mesons would continue to be massive. Or maybe a more dramatic way of saying it is that people sometimes quote this hard to understand, make this hard to understand statement that up quarks have a certain mass and down quarks have a certain mass. But then you add up those masses and you try to estimate the mass of the proton from there, and that doesn't work, right? Okay. It's because the mass of this bound state has its origin in the QCD coupling, not in the putative masses of the box. Okay, that's the other thing we see from this model. I mean, it's a very beautiful model. Every time you solve the quantum field theory, it's always very nice. We solve this quantum field theory. Fortunately, what's a bit tricky. Not completely. It's sort of nice. Okay. So I propose to end our discussion of two-dimensional QCD with this. So we discussed 0 plus 0 dimensional QCD, matrix integrals. We discussed 0 plus 1 dimensional QCD with adjoint matter fields. We converted that to quantum mechanics of free fermions, and we discussed 1 plus 1 dimensional QCD, in which we solved. Now there's another solvable problem in 1 plus 1 dimension, which is 1 plus 1 dimensional QED. So we discussed the limit n goes to infinity. There's another problem that's pretty simple, which is n equals 1. Not trivial, okay, it's not a non-attracting theory. It's solved by Schwinger. It's called the Schwinger. Now, if we're going to have these presentations, I would suggest the Schwinger model as one of the papers for a presentation. So we help out. I would have loved to talk about the Schwinger model. That's one model I like, but we need to go for it. Okay. So I think that this ends our discussion of 1 plus 1 dimensions. We have to graduate to 2 plus 1 and 3 plus 1 dimensions. Now, any questions or comments?
Sir, if you just look at the expression for alpha, which is like the denominator squared by g squared. So m square is coming into picture in some sense. It can't only depend on the.
It depends on m square as well. But at least if you go to energy scales large compared to this mass square, that's a sublime section. The first term is independent.
So we stress on the first term.
I mean, at large n. N is much larger than log n. Okay. So what we are saying basically is that if we're at there are two energy scales in the world. There's the scale set by the gauge coupling and the scale set by the mass. The scale set by the mass is irrelevant and energy is much larger than the mass. But the scale set by the gauge coupling is relevant at all energies. Okay? Actually, the analogy with string theory here, more than an analogy, the similarity of this solution to what you get by quantizing string is quite dramatic, quite striking. And of course, it's part of the motivation for a Toft to propose that large n gauge theories turn into string theories. Proposal that was made in the typically prescient way in the 1970s, and then was made concrete by minus n. Okay. Any questions? Okay. Let us move on then. We had one more clearing up operation from last time. This is Callan-Lehmann representation theorem. To jog my memory of the derivation, I first had to try to look up textbooks, but then I realized that we're in the modern age. The modern age, you need only to look up Wikipedia. So I did Callan-Lehmann representation theorem on Wikipedia, and there's a beautiful one-page derivation of the problem. It's remarkable. Okay, so I'm going to amplify slightly on that derivation and then give it to you. I have the feeling it's a bit different from the derivation I studied as a student. It's nice. Okay, so actually this gives me the opportunity of telling you something. A fact that is very nice and actually used a lot in the analysis of unit energy, scattering, which I would love to cover. But maybe if we really continue this course next semester, maybe. There are many things about field theory. There are many interesting things about quantum field theory that would be nice to discuss. But this is just about the structure of free propagators of field. So let me consider a propagator which is p squared minus m squared plus m squared, where we're using the mostly positive convention. Again, this is the propagator of the free scalar. And the propagator in position space is e to the power I beta x of dp where by p by 2 pi. Okay. Now, something that let me remind you of the pole structure of this propagator. Something we discussed a lot when we were discussing analytic continuation of Euclidean business. Okay. But let me remind you of the pole structure of this propagator. The pole structure of this propagator is like this. The pole, if this guy is positive, you get a minus. The poles in P0 have a negative imaginary part when P0 is positive, and a positive imaginary part when P0 is negative. Okay. So suppose we were computing this Fourier transform when suppose we were computing this. Now suppose I'm talking about P lower 0. Okay. So everything I've drawn the P lower 0. Then, so that e to the power I p dot x is simply e to the power I p0 x0 plus no funny signs there. Okay. Suppose we are looking at this Fourier transform. Let's look at it for many cases. So suppose we look at it when x0 is greater than 0. The first case.
Sir, we are working in Euclidean.
No. This is all Minkowski.
So there should be a little minus sign.
I would put P0 low. The minus sign is in the relationship between P0 lower and P0. Just to avoid having to talk about this. I'm working. Okay. So, suppose we had x0 greater than 0. Then this integral here can be completed. So, it's same old. We close the contour, the positive imaginary axis. If we close the integral of the positive imaginary axis, we pick up only in this contour. Okay? Now, picking up this contour gives us what? Picking up this pole gives us what? It gives us the following. All we have to do is to set P0 equals minus square root of pi squared plus mi. Yes?
P lower 0 would be negative. So for x not greater than 0, we'll close it in the lower half, right?
Well, suppose x0 is greater than 0.
Yes.
We're doing the integral over p lower 0. That is. This integral d for 0, d for p. P0 is just an integration. Okay? And its contour, its singularity is again. Yeah? Alright? So we get P0 is equal to
So what I meant was when we put in a negative sign, even for x naught greater than 0, there is a negative sign sitting in front of p naught x naught when we are doing the integral for p naught.
I didn't understand. Second, negative sign sitting where? In the exponent?
Yes. Like we
Simplify p dot x is equal to, let's p dot x. P dot x is equal to p mu x mu. Is equal to p0 x0 plus p1 x1. This is just true. Now we write this in terms of p upper 0. This is equal to minus p0 x0 plus p1 x1. Because p upper 0 and p lower 0 are related by a minus sign. Okay? It's actually a trivial thing, won't matter where, it's just a change of variables. Right? I've got an integration variable, you can call it p upper 0, you can call it p lower 0. Okay? It will not matter for anything. So, okay, I'm just happening to use it. Yeah. For convenience, I'm using p lower 0 as the integration variable. It doesn't change. Yeah, and of course, the two poles that get it, suppose we were working the p upper 0 plane. This pole would be this one, and this one would be that one. But they were just totally interchangeable. Okay, yeah. Okay, great. Fine. So, now, so if x0 is greater than 0, if x0 is greater than 0, then p0 is this guy. Okay, so what we get is the residue. So we get e to the power I into let's call this omega p, minus I omega p, this quantity I call omega p, minus I omega p x0. Okay, and then what do we get here? Here what we get is we plug, we're supposed to, okay, so how are we supposed to do this? What we're supposed to do is to write this guy as p 0 squared minus omega p into p0 plus omega p with an overall minus sign. Because this whole quantity here is minus p0 squared plus omega p squared up to the I epsilon. So we dealt with the I epsilon by taking the right. One. Okay. So we have to find the residue of this pole. So we need to take p0 is equal to minus omega p and plug it in here. So we just get minus 1 by 2 omega p e to the power minus I omega p x0. Okay? Now you see that we will get exactly the same answer if instead of this quantity here, we use the quantity delta of p squared minus m squared times theta of minus p. Suppose we do this integral for x not greater than 0. E to pi p dot x. Okay. If we did this integral, then what, we got two. The delta function clicks in two places, but only one of them is not vanishing given the theta of p0. So you get only the negative root. You get a Jacobian factor, which is 1 over derivative of p0 squared, so 2p0 modulus. So you get this quantity Oh, and this minus sign is also going away actually, because we've got minus in here. Okay, and maybe we need a 2 pi i. Maybe we need 2 pi i. Do you see that for x naught greater than 0, this Fourier transform, this Fourier space propagator is just the same as the statement that you stay on shell, but you take only negative lower P0 or positive upper P0 solutions. Okay? Similarly, now let's look at x naught less than 0. When we've got x naught less than 0, we have to close the contour again. We have to pick this guy up. Okay? So we get a minus sign, and we only get the contribution from the propagator, from P0 positive. Okay? Now, there's an overall minus sign here, which will kill that minus sign, because now we just get, we put omega p here, 2 omega p. So once again what we will get is 2 pi I times delta of p squared minus n squared, but this time theta of p0. Okay? So this fancy propagator that we're so used to writing, out here, actually has an alternate representation that makes its physics more transparent. It says that if you are interested in the Fourier transform for x naught greater than 0, all you have to do is put the on-shell delta function, but take the negative p lower 0 solution. If you are interested in the Fourier transform when x naught is less than 0, what you need to do is take on-shell momentum, but you flip. Okay? So, another way of saying it is that energy always flows in one direction. Always flows from, depending on which energy you're talking about, earlier to later times. Okay? This is actually very useful. It's clearly, this is true in every dimension. It's clearly a very useful way of thinking, physical way of thinking of the propagator. And as we will see, it will have, as we will see in our analysis of unitarity of scattering, it has very useful formal implications. So it's a useful factor. Okay, is this clear? Now, what we're going to do, once we've got this in our head, the Lehmann representation theorem is very easy to derive. Just by working with the two special cases. Let's work separately for x naught greater than 0 and x naught less than 0. So, this way we absolve ourselves of dealing with those horrible theta functions, which is the cause of all.
So how is it physically more transparent?
It's physically more transparent because propagation is entirely on shell. You see, this see, what was the ordinary propagation? It was 1 over p squared plus m squared. It has a peak when you're on shell, but it has this tail everywhere, and that's correct. But once you look at it in terms of x naught greater than 0 and x naught less than 0, that tail is entirely a consequence of the fact that you're switching which on-cell solution you're choosing. See, this function here is 0 away from the solution of the classical equation. It has no tail away from the on-shell. Okay? The only issue is that this thing here changes discontinuously depending on what x naught is. So if you want to write a uniform function, that is the Fourier transform at all values of x naught, you cannot do the entire equation.
So normally we say that these are the loops, they are called virtual particles because they are not constant, right? But this way of writing, like,
you see, that's the point. You see, this is only valid for x naught greater than 0.
yeah.
This is only valid for x naught less than 0. Now when you go to loop, you're only doing a momentum integral, you're not doing x naught. So there is one function whose Fourier transform gives both these results for both x naught positive and x naught negative. And that is the thing that,
Yes.
okay? But it's useful to know that there is a way of thinking of it that makes it very close to what's going on ship. Okay? Now we got this Riemann representation theorem. We want to look at phi x, phi y. We want to look at the time order thing. But let us first suppose that x naught is greater than y naught. Then phi x, phi y time order is just the same thing as this object. Okay? Now we repeat the analysis we did in the last class. We put a complete set of states here. We get this in terms of 0 by 0 n square. I'm assuming phi is Hermitian. Otherwise, I would take phi x, phi tangle. So that is what's going to be. Okay? Mod square times e to the power I can't remember the sign. P n interacting x minus y. Sum over n. Just by inserting a complete set of states. Now, the next step is this quantity here. Suppose I define the following quantity. I define delta of P minus Pn. Delta D of P minus Pn. 0, y of 0, n. Not squared. Sum over the whole spectrum of the theory. This is some function of P. Right? Okay? But by Lorentz invariance, it can only be a function of P squaring. If you boost, nothing changes. Okay? So this is some function of P square. Now, what I do is I define this. Right? I define this as equal to rho of P square times theta of P0. Okay. Firstly, what's going on? Yeah. Because PNs are energies of physical states. Physical states are always defined to have energies greater than 0. This quantity only has support when P0 is greater than 0. Okay, that's why there's this P0, theta of P0. Okay? And this quantity, whatever it is, some function of P square because of Lorentz invariance. Okay? Now, the next thing I do is the following. quantity, so this quantity here, okay, can be rewritten as dp times rho of p squared theta of p0 ddp rho of p squared times theta of p0 times e to the power I p dot x minus 1. Just by plugging in the definition. Okay. And then the next thing we do is to define rho of p squared. And the next thing we do is to write this as dp d mu squared delta of p squared minus mu squared rho of mu squared theta of p0 e to 5 p dot x.
So you do a variable.
I just introduce the variable and put a delta function. So it does nothing. Actually, this should have been upper zero. This is the upper zero is always positive. Upper zero. Theta minus 3. Okay? Now what does this tell us? This tells us that the Fourier transform for x naught greater than 0 is what? It's integral rho of mu squared d mu squared times theta of minus p0 delta of mu squared minus m squared. But this is exactly the propagator of the free boson propagator for x naught greater than 0, as we just derived. Is this clear? Okay? Now when you do the same thing with y and x replaced, suppose x naught was less than y naught, we would just get everything reversed, okay? And all that will change is that this theta will become theta plus p0. So, since we've done it for both cases, we sum it up and we conclude that the time ordered propagator phi of x, phi of y is equal to rho of mu squared d mu squared of the propagator for the free boson, and therefore mu squared minus m squared plus m squared. Okay, so this is the answer that will have the correct answer for both x naught positive and x naught negative. How you could get conflicts with unitarity causality if you try to do something. Okay, it's an interesting ongoing problem, not completely understood, but very likely the end story is that you can't do it. Okay.
Classically, there is some problem. It's only the problem lies with the quantum version of
Yeah, you could say it that way, right? Another way of saying it is another way of saying it is that we want to associate a Hilbert space with the path integral. Okay, and if you go back to the first lectures of this course, we found that anything that was x dot squared plus something, we had a very easy way of associating a Hilbert space. You try to generalize that to x double dot square, it just collapses. Okay? So you can write down a path integral. Nobody's trying to stop you from writing down an integral, but you have to associate a unitary Hilbert space structure with that by cutting that integral. Like we tried to do very carefully in our first few lectures. And even 9 is very difficult to do anything that right.
That picture isn't that like saying not able to quantize it, because not being able to build a Hilbert space picture for that path integral is like not being able to quantize.
Well, the path integral could be a conjecture for what the quantization is, right? Let's say we've got an action and we define our quantum theory by the path integral associated with that action. That is something that will allow you to compute all correlation functions. Question, does that definition give you answers within a Hilbert space? Does that definition give you, does that path integral define a transition amplitude in a Hilbert space with the structure of unitarity? This is now a mathematical question. The answer is either yes or no. Okay? And there's no reason to suspect that the answer is yes. In general. Maybe special cases the answer could be yes.
But then wouldn't it be the case only for like, because we could do that, the reverse, like Lagrangian to Hamiltonian, because we knew that we were like quadratic in P. That was the the reasoning behind being able to write the Lagrangian out of the Hamiltonian.
No, it's much more than that. It's that, you see, the whole structure of Hamiltonian mechanics is built out of position and a momentum. There are two pieces of initial data because the differential equations are set in order. You know, if you work with Lagrangian, let's say we've got a quantum mechanics, we've got a position. Okay? The differential equations of Lagrangian quantum mechanics are x double dot is equal to something. So the initial data we need to specify with evolution is x and x dot at some time, because the equation gives us x double dot. So there are two pieces of data. We trade those two pieces in building canonical framework of classical mechanics for x and p. So we go to phase space with the space parameterization of initial conditions. So x and p has this beautiful structure that easily lifts to the operator structure of quantum mechanics. It was very one that there were two. Suppose we had x triple dot is equal to as your equation. The whole structure, canonical structure of classical mechanics collapses. Okay? The whole Poisson structure collapses. There seems no natural operator structure to build. Now, none of this is a theorem that it cannot be done.
So if you get three initial conditions with x triple dot,
Yes. We would need three initial conditions.
Maybe the structure will be different, right? We won't get that.
But you see, we needed not, in order to make the Dirac correspondence between classical and quantum mechanics, we need the structure of phase space. We need a bracket. That is very strongly tied to the equation of motion being set. Okay? Now, none of these words are a statement that it cannot be done. It's just a statement that's not clear that it can be done. Okay? The sharp question is, you got some path integral. You want to interpret that path integral. You want to find a Hilbert space within which the path integral gives you an overlap of states by a unitary evolution operator. In the case that it's second derivative, we can often do it. In the case that it's not, I'm not saying there's a theorem that you cannot do it, but I think it's very likely that in general, you write out a general action, you cannot. Okay? This thing here, though, is theorem. It's telling you that in unitary quantum field theory, the propagator has to fall off like 1 over p squared. What that means in the end is up to you to understand. But certainly it seems somehow inconsistent with having higher derivative terms. Okay? None of these are type things, okay? You should be wary of them. But they're all pointing in the same direction. This, by the way, was tried a lot in. This is part of the reason why it's tough to make tough to make sense of quantum theory of gravity by just putting counter terms. So one of the attempts that some people did was to try to take quantum gravity with r plus r squared. Now r squared has 4 derivative terms in the kinetic term. Okay, and so tames the divergences of that you can get in relativity, because your propagator is goes like 1 over p squared goes like 1 over p to the 4. Okay, because the propagator falls off faster, your divergences are better, and you can actually define a renormalizable theory of gravity with an r plus r square action. But the point is that it tames it in precisely the wrong way. It tames it by making the propagator 1 over p to the 4, and therefore more or less guaranteed to be inconsistent with unitary, as detailed analysis shows that it is. Okay? If you now try to remove this fact, somehow, it's very likely that the divergence will come back. You see? So, taming divergences by propagators falling off faster is a very dangerous thing to do. Okay? This is a very interesting general subject, which I don't think the last word has been written about at all. But let's move on. Other questions or comments? Okay, so this was the I want to continue from this Lehmann representation here. This is the structure of the Lehmann representation. Now, the last thing that we want to understand is what is rho of mu squared. What is rho of mu squared? What rho of mu squared you get from a spectrum of single particles. So suppose we had a spectrum of single particles here. Okay? Suppose we had a spectrum of single particles here, then what is the end label? The end label is just the momentum. Okay? So the end label here would just be the momentum, and there would be a state here for every value of the momentum. Okay? So this thing here would just be 0, phi of 0 times momentum, and the sum over n would just be d3p. And then we would have to put delta of p minus. Okay, so let's call this some q, d3q, and delta of p minus q, where q is the form momentum where the energy part of q is on shell for this particular single particle state. Okay? Now this quantity we understand, right? This quantity we understand either by Lorentz invariance or just by doing the calculation of free field theory. Okay? This quantity is just proportional to 1 over omega. You know, in free field theory, for instance, this is the case. Okay? So we can just compute this. Plug this into the definition of rho of p. Okay? And you see that actually what we're going to get is just rho of p is equal to a delta function. Because all this thing is doing here is putting the energy part on shell with this 1 over omega q factor, which is precisely what you get if you had a delta function. A delta function saying that p squared must obey the mass square condition of your free particle. Okay, this would be the Jacobian, and this is putting it on. Okay, so I went through that very fast. You can easily do it more carefully, and just check that if you insert the spectrum of a free particle in here, what you will get as a contribution for rho of mu squared is a delta function at the value of the mass of the free particle. Rho of mu squared would be mu squared minus m squared, delta of mu squared minus m squared. Okay? So, we've seen that this general structure arises, and we've also seen that the contribution to rho of mu squared from n being a single particle spectrum is folds. I'll leave it for you to verify that if you take a two particle spectrum, you get a cut. You can just try to work out what rho of mu squared is, for instance, for a simple operator. Okay? So this is really all I wanted to say. Stage of lemma amplification. Any questions or comments about that? I'm sorry, this last part is not too fast. But it's still okay. Any questions or comments about this? Okay, fine. So in the next class I will turn to a study of Young's theories in 4 dimensions. I don't know much. I don't have much to say about Young's theories in 3 dimensions. There's very lots to say about Chern-Simon's theories. Young's theories in 3 dimensions. This work of the guy called Nair was trying to guess the ground state of the theory using a variational approach. And it's quite interesting, but it's totally uncontrolled. I mean, it's a guess which, it's not like there's a parameter that justifies it, so I don't think it's worth presenting in a class. Okay. It's sort of interesting, okay, but okay, fine. Right, so I think we just move straight to 4 dimensions. Maybe we don't have much to say anyway. But
Chern-Simon's theories.
what? You want to study Chern-Simon's theories? I'd love to. I'd love to, but a core course of quantum field theory should cover something. I wanted to discuss anomalies, instant terms, and so on. Maybe Chern-Simon's theory will postpone. Okay, it's okay. Maybe, yeah. It's something I'm working on, so I would love to talk about it. But I think you should. There's some basic foundational material that one should get through before moving on more accidents. This is for the camera, which has come late for this class. We're just clearing up. We're just clearing up. Thanks, guys. No, it's no problem. We're just clearing up confusion from last class about the index structure of this integral equation. So we're defining m alpha beta to be psi alpha psi bar beta in the presence of one insertion of psi bar. G alpha beta, the exact propagation to be psi alpha psi bar beta with the presence of 0 insertions of psi bar, just the exact propagation. Okay? And with these definitions, it's not difficult to convince oneself that the right structure of the integral equation is this: that m is equal to m0, g gamma minus m gamma minus g. That's the right index structure where multiplication is just by matrix multiplication, where you treat the lower index as the first index and the upper index as the second index. It's just straightforward matrix multiplication of this object, where an m0 is just g times g. Okay? Now, as we look, when we get this index structure here, it's clear that the only part of m that can contribute is the part proportional to gamma plus. We call the coefficient of m that is proportional to gamma. M could be anything, but the only part of it that appears on the right hand side is the part proportional to gamma plus, and we call the coefficient of that m minus. Okay? So the only thing that appears on the right hand side is m minus. So if we want to solve the equation for m, let us first solve the equation for m minus. Once we have m minus, to determine all other components of m is trivial, because we just have to work out the right hand side. Once we know what m minus is, then m is determined from this equation. this equation is a complicated equation because the unknown appears both on the left and the right hand side. But as we've seen, the only part of the unknown that appears is m minus. So once we know m minus, our problem is easily solved. So it boils down to just determining m minus. Okay? So we're only interested in the minus component. So we're interested in the part of this equation that is proportional to gamma minus. So what contributes is the part proportional to gamma plus. Gamma plus. Right. So we want the part proportional to gamma plus in this equation. You remember as we argued last time, for the singularity we can forget about n0. We just need this homogeneous equation. Okay. So we want the part proportional to gamma plus. When you see this term, even if we take the part proportional to gamma plus here, for the whole thing to be proportional to times integral phi of p minus plus k minus or over k minus squared b k minus divided by m squared by 2 b minus plus m squared plus m squared by 2 r minus p minus plus c squared by pi lambda plus r plus, where lambda was the infrared cutoff. You remember we were taking the integral and just stopping it where the propagator, the gauge was on propagator, the momentum the gauge was on propagator reached lambda. Okay? This was the infrared cutoff in our exact computation of the propagator. What was capital M? M square was the effect of renormalized mass. Was it? M squared minus G squared by 1. You remember when we solved for the gauge boson propagator, for the fermion propagator, we got one correction term that just renormalized the mass, and then the other correction term that was infrared divergent. Okay? So now we're working in terms of this renormalized mass. And then we have this additional ugly infrared divergent case. Okay? So n squared is written in terms of the bare mass squared where this object is. This was the integral equation we got. Someone remind me where we get this theta p minus theta r minus p minus. Somebody? Why? Gamma plus. We need the part from G. That's proportional to gamma plus, and this G also proportional to gamma plus. So that we have 3 gamma pluses, 2 gamma minus, so that the next charge is plus. So the whole product will be gamma plus. Okay? And that gives us exactly the equation we wrote down last class. See, the part proportional to gamma plus here comes with K minus. Part proportional to gamma plus here comes with K minus. You look at your notes, that's the equation we wrote. We took the part of the propagator for the fermions proportional to gamma plus, the part of the propagator fermions proportional to gamma plus, and just multiplied it through. And that gave us the integral equation that we wrote down in classes. Okay? This integral equation that that had a factor of p minus minus r minus and p minus in the numerator. Because the part p minus came from P minus gamma plus. P minus minus R minus came from P minus minus R minus. Is this clear? Okay. So this. Okay. Once we've solved for M, and the key point is that this is the only non-trivial solving process. The only place where you have to invert something, and thereby the only place from which you can get a singularity. Okay? Once we've solved for M minus, all the other components of M will be easily determined, and the procedure that determines them has no possibility of generating new singularities. So all singularities in the two-point function can only come from singularities in the solution for M minus itself. And therefore, if we are interested in the spectrum of the theory, we need only study the singularities of the operator of this N minus, or in other words, the zeros of this homogeneous operator. Is this clear? Questions, comments? Okay. By the way, if we didn't want to throw away this part, it would be easy to keep. We just keep G, G, K minus, K minus. Okay, just keep the part proportional to gamma plus from here as well. Okay, we're not interested in that, because that would also be easy to keep. Okay, so this just justifies the calculation we did in class last time. Everything else we said about the integral equation is correct. There's something I got confused about with the index structure, which I hope we've cleared up now. Any questions or comments about this? Okay, let's complete our analysis of this model, and then I'll come back to the second confusion we had last time about the derivation of the Lehmann representation. But just to not break the discussion, let's finish this discussion and then come back. Okay, any questions or comments about it? Sorry for the mess up last time, that was not a good thing. Sorry about that. Okay? Excellent. So, now at the end of the last class, we achieved the following integral equation. You remember that we called the coefficient of this gamma plus in M, we call that coefficient psi, and then we take a certain integral of this psi, an integral over P minus or P plus, P plus, or integral over P plus, and we call that phi. Everyone remembers this? And we had an integral equation for this phi. And you remember that we processed that integral equation, and one very nice thing happened. The very nice thing happened was that there was a new singularity in that integral equation. A new IR singularity coming from an integral of phi with a 1 over P minus square. That had a new singularity at the denominator of that kernel, and then we wrote that kernel as that integral, which was just some integral. Is this making sense? Everyone's actually looking. No, people don't remember this? Yeah. You remember we had that there was an equal. Firstly, you remember that phi, by polar manipulations. Okay, let's just remind you. Okay, so there's this exact M. It has a momentum that runs through, which we call R, and then the division momentum. Okay, so if we call this momentum P, this was R. R was constant at each step in the integral equation. R was just constant. R was not a variable of the integral equation, it was just a parameter. P was a variable of the integral equation, because if you've got this guy here, then you look at this, if this is some P, this would be some other P, and the P is being integrated. Okay? So it's like a matrix equation where the matrix variable is P, and R is a number. Okay? And what we had found was the integral equation phi of P minus R minus was equal to G squared by 2 pi theta of P minus theta of R minus minus P minus time. Somebody, where do we get this?
Positivity of energy and R greater than R greater than.
Where in positivity or in? Go on. Yes, go on.
Since R is the total energy, means R minus is the total energy you want at each P minus you want R minus to be, it will be greater than P minus.
You give it a good physical interpretation, but we got it from mathematics. How to, what you're saying is actually completely right, but where did we get it from? We got it at a certain step. In the integral for psi, in the integral equation for psi, we had no thetas.
Yeah.
We got a theta function when we moved to the integral equation for phi. Okay? What did we do in going from the integral equation for psi to the integral equation of phi? We integrated over P plus. Now, you see the integral equation on the right hand side has these two fermion propagators. And we have P plus enters only in those two fermion propagators. Because the gate boson propagator was entirely a function of P minus. Okay? So we have to integrate the two fermion propagators over P plus. But now look. Remember, because we're working in light cone variables, the denominators are linear in P plus. So if we were working in ordinary time, the denominators would have been quadratic. But P square is P plus P minus. So it's linear in P plus. Right? We've written out after integration. The denominator is linear in P plus. So what we've got is a product of two poles. And we did the integral by contour means. But remember that the coefficient of P plus was P minus. So we got P plus into P minus, and then we had R minus, let's say P plus minus R plus into P plus minus R minus. And this was Sandara plus I epsilon. This was Sandara plus I epsilon. And we were doing integral dP plus.
Inside the contour.
Exactly. Now the point is that P minus and P plus minus R minus are of the same sign.